So I'm going to talk about accusations against transmathematics. This is not accusation theory. This is actual accusations, false claims that have been made about transmathematics. And I was prompted to write a paper on this and this presentation when someone wrote down the accusation and made it public that Transreal Arithmetic had plagiarized IEEE 754 floating point arithmetic. The paper is in Transmathematica and it deals with the history of Transreal Arithmetic. So we can answer the accusation by saying, well, no, we didn't plagiarize it. It has an independent history recorded in the literature over 10 years. And the paper also points out differences and faults with the existing floating point arithmetic. So I want to discuss various accusations that have been made over time. In particular, the claim that we plagiarized floating point arithmetic, and as a positive exercise from this, show how floating point arithmetic could be improved. Perhaps this account of accusations will provide material for Jan and his friends to analyze. So Transreal Arithmetic was developed from 1997 to 2007. It took 10 years. All of the accusations were first made around 2007 when the first proof of consistency was published. So for 10 years, there were no accusations. Everything went along very quietly. Suddenly, there was a proof that dividing by zero is consistent. And there was tremendous reaction across the world and many accusations were made. Only 2 of those are still repeated. Now, it's worth noting that all the accusations against transmathematics relate to transreal arithmetic, not to transfields, transvectors, transboolean logic, transcomplex or transquaternion arithmetic, transreal or transcomplex elementary functions, transreal or transcomplex analysis, transphysics, etc. And I love the fact that there is an etc. Transreal arithmetic has led to a lot of developments, but the only one that receives accusations is transreal arithmetic, the easy one. No one brings accusations against the more complex material. People do criticize the more complex material, and that's a perfectly valid thing to do, to analyze it, to say it has these benefits and disadvantages. But no one levels accusations against those more complex mathematics. Now, I've had a very wide range of accusations, one of which was made by a number of people, was that transreal arithmetic will destroy the world. And my immediate assessment of that is, well, there's no evidence that this is true. And I formed the opinion that people making this claim were insane. Now, insane people are not necessarily wrong. So I invite you, if you believe that transreal arithmetic will destroy the world, to use transreal arithmetic to destroy this carving, which is a copy of a Celtic cross. And as soon as that is destroyed only by transreal arithmetic, I will take the claim seriously. Now, what am I to do, a scientist, faced with people who say that I'm going to destroy the world for what are clearly insane reasons? Well, my response is to say that there's likely to be a benefit to the world by doing what I am. And the benefit is the benefit of of total systems, which remove the necessity for error. If you have a partial system, you're guaranteed to have an error somewhere. if you have a total system, you're not guaranteed to have an error. Modulo what Bass said about the universe being so complicated that everything runs into trouble somewhere. And unsurprisingly, these accusations ceased. People didn't take them seriously anymore. They did amusingly produce various pieces of artwork. So you can see pictures of the worlds being destroyed by division and by zero, which is rather amusing. So something positive came from these. Now, the second sort of accusation was transreal arithmetic has some property. For example, nullity is absorptive. People say, oh, transreal arithmetic is terrible because nullity is absorptive. And my response is, well, so what? What does it matter that nullity is absorptive? And my so what is prompting my accusers to give a reason. Nullity is absorptive, so what are the bad consequences? And if anyone has bad consequences of nullity, then I would like to hear them. I didn't give any response to this. There are lots of these claims that cover all sorts of areas of science. To give you an idea of the size of the problem I faced, within 24 hours, 100,000 people raised accusations against transreal arithmetic. I cannot respond to 100,000 people. 1,000 of them contacted me directly. And it took me many weeks to reply to 1,000 people and their accusations. And I did actually reply to those 1,000 people. They sent me emails. I replied to everyone giving my reasons. And this was 2007. It was before we had the idea of trolling. So I was actually being trolled by 1,000 people. I didn't recognize it for what it was, trolling. I thought it was serious scientific inquiry, and I replied in a scientific way, which turned out to be the wrong sort of thing to do. The accusation is that transreal arithmetic is inconsistent, and people gave proofs of the inconsistency. I examined all of their proofs, there were a lot of them, and found that they were all faulty. And I spent a lot of time looking at reasons why people, out of the proofs, why people think division by zero is impossible. And that helped me to understand where people are coming from, what their understanding of mathematics is, and to understand their worldview. So I now have a very good idea of why people believe that division by zero is impossible, and that makes it easier for me to engage with them and show that division by zero is in fact a reality. And it's a reality that has been known since 1957. So work I did with Jan, looking at Soup's approach to division by zero, is actually an extremely simple method of dividing by zero, and one that's easy to explain. So by examining all of these claims, false claims of the impossibility of division by zero, I built up a repertoire of how to apply division by zero in mathematics in the world to take advantage of it. So this accusation was extremely useful to me as a scientist because of the work I put in answering the accusation. The accusation was, however, exceedingly damaging. Many people believed that transreal arithmetic was inconsistent. And there was one individual who made it his life's work to go around the world saying that transreal arithmetic is inconsistent. And he caused a tremendous amount of trouble. And then he died. And that was the end of the accusation. So simply by waiting, my accusers disappeared. There is a saying in English that science progresses one funeral at a time. And in that case, sad though it is that my accuser died, it certainly ended the accusations. Now, there was an accusation that transreal space is not compact, and that really surprised me that anyone would have a topological opinion on transreal space at the point where it was first announced in 2007. And they gave a proof. I looked at the proof, decided it was faulty, and at the time I did nothing about it. I just left it. And then working with Thiago, hello Thiago, we did loads of work on real analysis, transreal analysis, and amongst other things, proved that transreal analysis contains the whole of real analysis. And as a tiny, tiny part of those developments that took many years, we proved time and time again that transreal space is compact. So I didn't answer my accuser directly. I didn't respond to my accuser at the time. I just let Transmathematics develop into a great big steamroller that then dealt with the accusation. And the result is that that accusation has ceased. And if I hadn't mentioned it today, everybody would have entirely forgotten about it, and it would be a dead accusation. It's what I'm telling you in these few examples is ways that accusations can die. They can time out, their life cycle can end. Now, another accusation was that nullity is identical to bottom. I looked at that accusation. There is no evidence for it. So the people who say nullity is identical to bottom don't give evidence. Maybe they think the evidence should be self-explanatory. Now, I assessed this and decided it was false. And I told my accusers this is false because the numerator of nullity is 0, but the numerator of bottom is bottom. And you can see that those two statements have a different structure. Nullity and 0 are different numbers, but bottom is the same as bottom. So there is no way that nullity and bottom are the same thing. And this turns up again in other examples. So an early proof was that nullity, 0 divided by 0, is equal to 0 to the power 0, is equal to infinity divided by infinity, is equal to infinity minus infinity. And people accuse transreal arithmetic of simply defining what was already known as undefined. And that's not what transreal arithmetic does. Transreal arithmetic defines 0 over 0 to be a number, and then applies the rules of arithmetic and discovers that things which were previously undefined are now nullity. So nullity is not the same as undefined. By definition, I define nullity equals 0 divided by 0. Well, these accusations ceased as well. Now, a more difficult accusation is that nullity is an error value. And again, people who make this claim don't give evidence. And I interpret that as an opinion. So people, scientists, mathematicians, or whatever, are of the opinion that nullity is an error value. And this is about to lead us into a very deep and important insight. And my response is that this is not true because, and notice that I'm saying because. My accusers say nullity is an error value and there's no because clause to their statement. I'm saying nullity isn't an error value, it's a number because, and my because is, it arises as solutions in geometry, trigonometry, algebra, calculus, and Dedekind Cuts. Nullity is a number for the same reason that every real number is a number. and we'll discuss more of those examples as we go through this talk. The second thing is that Newton's laws of motion apply to transreal arithmetic. We know what a nullity force is. We know how to apply it. We know how to write computer programs that control machines in which the control signal is nullity, or which the measured signal is nullity. Nullity is not a meaningless value to us. It's not undefined. It's not an error value. It is just a number that obeys the formal rules of transreal arithmetic. And that lets me reach out to my accusers and say, well, we both agree that transreal arithmetic is a formal arithmetic. We both know how to calculate with nullity. You believe it's an error value, which doesn't affect anything in the arithmetic. It affects your applications of the arithmetic in the world. And I have a different view. My view is that nullity is meaningful. I can do physics with it. I can apply it in the world in cases where you would not even try. So I put it to my accusers that they are accepting failure in the world where they do not need to. And that's always the case with partial systems. Partial systems are guaranteed to fail. Total systems are not guaranteed to fail. And this accusation continues. And I deal with that accusation in the paper. Now, this is a battle I need to win. In order to show that transreal arithmetic is useful, I have to show that nullity is not an error value. But it's not a battle I need to fight. I've already done enough to say, your position is that nullity is an error value. My position is that it's not. And now I'm rolling out a whole bunch of mathematics and physics that supports my position just as a tiny detail. And let me say that I'm completely happy for people to criticize nullity, even to make the claim that it is an error value, if they can justify that claim. Now, one exceedingly damaging accusation was that researching and teaching transreal arithmetic is unprofessional. I was a university lecturer, and this accusation was repeatedly brought against me. And my assessment of the claim was that it was wrong, that I was doing work in a professional way. I was a fellow of the British Computer Society. I went through the biannual accreditation with the British Computer Society as a chartered scientist. So I was meeting the professional requirements of being a scientist. I went through the biannual appraisal in the university, which shows that I'm meeting the professional requirements of teaching and research. I obtained grant money to research this topic. I obtained the approval of the teaching boards to teach this material. I got the approval of the external examiners to examine it. So my argument is that my teaching was entirely professional. And furthermore, I said that my teaching and research is likely to benefit the world, ultimately by promoting total systems. But in the end, I resigned, and there is a story behind that, which is probably best discussed behind closed doors. When I left employment, then, of course, the accusations ceased. And that has now left Brazil as the leader in university research and teaching of transmathematics. Hi, Tiago. Where's Walter? You guys are now the leaders. Now, it needn't have been that way. I had a colleague in my department who completely understood transreal arithmetic, and he wanted to teach it because it was a benefit for his own subjects. It would be better to use transreal arithmetic than real arithmetic in the things he did. but he was afraid to teach it because of the toxic environment, because of the accusations around transreal arithmetic. Now imagine if he had taught it, and he's still there, he could still teach it today if he wanted to. There would have been 2 members of staff teaching this material in a department. So students would see that it's not simply the views of one maverick member of staff, but it's got some traction within the department. We might have had more exchanges with Brazil. So there was a very little amount of exchange of staff between Brazil and my university. We could have built a core of examining transmathematics, but because of the accusations, that didn't happen. And I do wonder if I should have tackled the accusations earlier on. Should I have fought back earlier on? And I deliberately decided not to, because I thought I would be fighting little battles all the time. And I preferred to spend my time concentrating on the big picture, building up the results of transmathematics. So you can't change the past. That's what I did. That's the position we're in. Let me now switch to the floating point accusation. So I was accused of plagiarizing floating point arithmetic, and there is no evidence for this claim. It's an evidence-free accusation. It's an accusation that is made anonymously. People chat about it behind my back. They don't challenge me on it. And for a little while, for a long while, for many years, I didn't know that this accusation had been made. And then in 2022, someone wrote the accusation down, and I had proof that this accusation exists. That's a point that Jan made in his talk, that if you've got an accusation, write it down and it can be discussed. So I now have it in the literature that the claim that transreal arithmetic plagiarized floating point arithmetic. Now, at the time I first saw this accusation, which was around the 2007, around the time of the publication. Remember, for me, that's 10 years after I started research on transreal arithmetic. I decided there was no evidence in the accusation, so it's not a scientific accusation. I put it down to people who are not mathematicians, not scientists, that they were saying this, and I didn't have to respond. And furthermore, it's contradicted by the published papers. There is a literature of 10 years of how transreal arithmetic was actually developed, and at no point does it take inspiration from floating point arithmetic. So what was my response to this? Well, when people make this claim, you have plagiarized, I respond by saying, your claim is libelous. You are breaking the law when you make that claim. And I state the foundation of transreal arithmetic is 3 things: projective geometry, trigonometry, and calculus. And that's in the recorded literature. You can read the history of its development and see that that is true. And I advise people to read the published papers. Now, this accusation continues. It continues to this day. I respond to it in the Transmathematica paper associated with this talk. And it's extremely damaging. It's damaging to me. It limits what I could do when I was a teacher, university lecturer. It limits people's take-up of transmathematics and the things it could do for them. There are areas of science where there are significant benefits that are very easy to obtain, and people don't do it partially because they believe these accusations. So it is a serious accusation. So this is one that I need to win in order to make transmathematics accepted, and it's one I need to fight. I need to come out and say, you are being libelous, you are not being scientific with this claim. And we'll come to how I intend to fight back. But the first thing is simply to state the history of the development of transreal arithmetic. Right, here we have a picture. So transreal arithmetic derived from projective geometry. This is a fairly naive picture of what's going on in projective geometry. We have a projection point, rays of light pass through the projection point, and we see objects in the world. Objects on one side of the point turn up upside down on the other side. And there are many geometrical models of projective geometry. And they all have the property that you can point to the points at infinity on the horizon. So if I'm standing on the beach looking out to sea, I can point and say, in that direction, there is a ship on the horizon. Now, nullity, in all of the models of projective geometry, I can touch it. Here it is. Nullity is a point in a geometrical construction, and that makes it a number. So when the ancient Greeks were developing mathematics, they worked in terms of geometry, and their notion of a number was anything that can be measured. And here it is, I am touching nullity. Nullity is a number for the same reasons that every real number is a number. Right, projective geometry, it's a particular kind of geometry. It has the property that the projection point is nullity, 0 divided by 0. And it has infinities of the form x over 0, where x is not equal to 0. And those infinities occur on the horizon. So there's a lot of infinities. Every real number other than 0 divided by 0 is an infinity that occurs somewhere on the horizon. Now, there are two ways to do projective geometry. You can do it with a single cover, which is a single copy of projective space. And in that case, all the points along a ray are considered identical. They're considered identical because if you put up a screen and look what's on the ray, it doesn't matter where on the ray the object is, you will still see it at that point. So every point along the ray is considered identical. So in a single cover, points are identical over a non-zero dilatation. And that means that nullity is unique, and it means that unsigned infinity can have the canonical form 1 over 0. We could pick any value of x and make it canonical. It's convenient to pick the value 1. The other way of doing it is to have a double cover so that points are identical along a ray over a positive dilatation. And that gives you two infinities, a signed infinity plus infinity equals plus 1 over 0, minus infinity equals minus 1 over 0. Now, as a rule, mathematicians prefer the first version, a single cover, because it has a simple algebraic structure. And as a rule, computer scientists prefer the second one because it allows them to do computer graphics. If you're going to make a film of Who Framed Roger Rabbit, it really matters what's in front of the camera as against what's behind. So mathematicians, if they were making a film, would show everything that is in front and behind the camera at the same time, whereas computer scientists are only concerned with what's in front of the camera. It's a perfectly understandable distinction to draw, and it's a distinction that has a mathematical basis, an underpinning in topology. So it's lucky that I was a computer scientist and knew both of these approaches to projective geometry. And the really important thing is to say that nullity and infinity, however we conceive them, are numbers because they arise in a geometrical construction. They are numbers because the ancient Greeks decided that that's what numbers were, points in a geometrical construction. Numbers are not error values. Numbers are things you calculate with. You might like the number you calculate, you might dislike it, it might fit with your model of the world, it might not, but it's not an error value. It's something that you can calculate with a formal arithmetic. And at that time, in 1997, I chose nullity as 0 over 0. There's no other choice. Nullity just is that value. There is a choice about infinities, and I chose to use signed infinities. Plus and minus infinity equals plus and minus 1 over 0. So that was 1997. That was when this research kicked off. Now, in 1999, 2 years later, transreal arithmetic defined the arithmetic of transreal numbers was defined over addition, subtraction, multiplication, reciprocal, and division, as we have it today. And ordering was defined via the relationship A is greater than B if and only if A minus B is greater than 0. That's a completely standard way of defining ordering. So in 1999, 2 years after I came across infinity and nullity as elements of projective geometry, I then had a complete arithmetic. And there's quite a story of how you get from projective geometry to an arithmetic, but that's too long for today. Now, in 1999, I published those results in a conference on numerical methods. And I was looking at Jacobi's algorithm for liberating eigensystems. I was using transreal arithmetic to calculate the solution. I was doing it with rational arithmetic, so there was no increase in error during the calculation. And what I discovered was that Jacobi's original algorithm allows division by 0. And when you perform division by 0 in the algorithm, using transreal arithmetic, you get the correct answer. You correctly liberate the eigensystem. So how is it that Jacobi, writing in the 19th century, could set out an algorithm that allows division by 0 and get it right? And the answer is that he was reasoning geometrically. Geometrical solutions define that any point in the construction is a number. The number 0 over 0, the number any real number divided by 0, occurs in Jacobi's trigonometric view of his algorithm. And this is a bit of a shock to people. Real arithmetic does not, cannot describe the whole of geometry. Not the number nullity, the numbers infinity do arise in geometrical constructions. Okay, so how did I know that? How did I know what Jacobi's original algorithm was? If you look in modern textbooks, they do not correctly describe Jacobi's algorithm. In the innermost part of the algorithm, there is a choice. And it says, if you're about to calculate a tangent with a 0 denominator, switch instead to a calculation using the cotangent. And that avoids the problem of division by 0, except in one case where you've got 0 divided by 0. Okay, but I had access to Jacobi's original algorithm. How did I do that? I went to the library. I found Krell's journal, where Jacobi's algorithm was published. It's published in German with a Latin abstract. I can understand a little bit of Latin. I understand quite a lot more of German. I could read it. So when I pulled this volume of the journal off the shelf and opened it, dust came out of it, and it set me to coughing, as you might imagine in this situation. And I took it to the front desk to borrow it. At that time, you had to speak to a librarian to borrow books. And she asked, do you want to borrow this book? And I said, well, yes. So she opened the journal. This is a 19th century journal. and she stuck a piece of paper on it and stamped it. I was the first person to borrow that volume of the journal in 200 years. Well, 150 years. That's how I knew what Jacobi's original algorithm was. I read it in German in a 19th century journal and discovered that Jacobi allows division by zero. He allows division by zero because he didn't think to deny it. Prior to Dedekind, people pretty much didn't bother to say you must not divide by zero. If you look at Newton's works, he doesn't bother to say you can't divide by zero. The arithmetic he sets out is consistent with transreal arithmetic, is consistent with other things as well. I don't want to spend too much time on this. He had a different view of equality. But Newton's method of calculating forces works for real and infinite forces, but does not work for nullity forces. And it doesn't work because Newton assumed that you can draw a force diagram on a 2D sheet of paper. And that's not always the case. Sometimes nullity arises, which lies off the sheet of paper. And there is a geometrical construction which will rescue Newton, and that's what gives us the extension of Newton's laws of motion to transreal arithmetic. That's a long story in itself. So in 1999, I was told about, I read an ancient Greek formula dating from about 400 BCE that gives all the right triangles that have integer solutions. Yeah, I'll change that slide. So it gives all the integer solutions for right triangles, and it's set out in terms of parameters. And using transreal arithmetic, you can set those parameters equal to nullity, infinity, an unsigned infinity to a signed infinity, and it gives you a solution. So here is some mathematics from 400 BCE that allows division by zero. Why does it allow division by zero? Because it's geometry. And infinity and nullity can occur as points in a geometrical construction. So yet again, nullity and infinity are numbers for the modern reason that they are solutions to an equation. They have exactly the same status as any real number. They can occur as a solution to an equation. Then in 2002, I replaced the number minus infinity with the asymptote minus infinity. That was a terrible mistake, but I did it because I wanted to simplify transreal arithmetic, and by having only one infinity, and I wanted to explore trigonometric functions, power series, and so on. In 2006, I reintroduced negative infinity as a number. So I wasted 4 years on that, but it was a useful thing to do because of all the exploration I did. I was pushing the boundaries. I've got, from projective geometry, I have a notion of what transreal arithmetic might be, and I'm expanding it and contracting it, trying to make it just precisely the right extension to real arithmetic. And tetrachotomy, and I also developed the idea of tetrachotomy, which is to say every number is exactly one of less than zero, equal to zero, greater than zero, or equal to nullity. And that replaces the usual trichotomy of mathematics. And it turns out this is critical. Tetrachotomy is the Rosetta Stone. It's what explains what a nullity force is. So a nullity lies off the transreal line. The transreal line can be divided up, extended real line can be divided up with trichotomy, less than zero, equal to zero, greater than zero. Nullity can't, it lies off the line. Therefore, it lies outside the extended real universe, and the nullity force projects into the extended universe, into our universe as a zero. but it's a delta zero, not an absolute zero. Again, a long story behind that, but it means that we know what infinity and nullity forces are, and physics develops from a notion of force to a notion of everything else. We are in the position that we could, if we had enough time, extend the whole of physics to allow division by zero. In 2007, I, with colleagues, Andrew and Norbert, produced a machine proof of consistency, and in order to do that, I had to come up with an axiomatization of the arithmetic, and I adopted the maxim that transreal arithmetic is the least change from real arithmetic that allows division by zero and supports the whole of real analysis. So that was my rationale for developing transreal arithmetic. I now had a view of what transreal arithmetic was good for. So at this point, I had been working on transreal arithmetic for 10 years. And once the consistency proof was published, I decided I will make this my life's work. I was about 50 at the time, so a bit late for identifying one's life's work. But I'd already spent 10 years since I was about 40. So Thiago is always interested in how I got into transreal arithmetic. I drifted into it for 10 years. And then after I'd accumulated 10 years worth of success, I decided to make that my goal. So in retrospect, it had already been my goal for 10 years by the time I recognized it. Right, floating point arithmetic has, I do find it fun trying to say this, 9 quadrillion, 7 trillion, 199 billion, 254 million, 740,990 error states. That's how many nans there are in 64-bit arithmetic. It is 25,000 error states for every star in the Milky Way galaxy. It is genuinely astronomical. When I started my research, it was 100,000 error states per star in the Milky Way, but over the decades, telescopes have got better, and now astronomers know that there are 4 times as many stars in the Milky Way as they thought they were. Some floating point numbers are not embedded in the real number line, and that makes it hard to use real analysis to develop an algorithm. It makes it hard to use real analysis to develop a program because there are these values that do not occur in the real number line. And having this many error states halves the accuracy of floating point arithmetic. Now, you need to read the paper to see how that works out. It's a detailed argument. We need to be clear what we mean about accuracy, but it is a true statement. Floating point calculations would be twice as accurate if you use trans-floating point numbers in place of floating point ones. Right, so what's wrong with IEEE 754? Well, first of all, there are a lot of nans. Let's call them nan sub I. And by definition, nan sub I is not equal to nan sub I. So that breaks the law of identity. That's bad news because classical logic and Boolean logic don't apply anymore. They assume the law of identity. If that law isn't operational, then you cannot specify or test floating point programs at the level of abstract data. Have you ever wondered why your floating point programs don't work? It's because it is impossible to specify them at the level of abstract data. It's impossible to test them at the level of abstract data. What you can do is specify and test at the level of bit patterns, and the details are in the paper. IEEE 754 also has -0 is equal to 0. That's good. The world will agree with that. But it also has 1 over -0 is not equal to 1 over 0, and that breaks the law of identity. So again, you can't apply Boolean logic to the specification and testing of floating point programs at the level of abstract data, at the level of saying there is a value 0. You have to go lower and look at what are the bit patterns that you are using for zeroing. every abstract nan I has two concrete representatives. It has one with the sign bit clear and one with the sign bit set. I've called them nan I plus and nan I minus. So every nan orders before and after every infinity, every real number, and every abstract nan, including itself. So let me show you a picture. Here's nan minus. It orders before minus infinity. It orders before minus 0. It orders before 0. It orders before infinity. It orders before nan I plus. But nan I plus is the same thing as nan I minus. So it orders before itself, and now symmetrically, nan I plus orders after infinity, after 0, after minus 0, after minus infinity, after minus nan I minus. So nan, every abstract nan, orders before and after every floating point value, including itself. But that means that ordering of abstract floats is inconsistent. It's impossible to specify and test a sorting algorithm that uses abstract floating point values. You can do it at the bit level. And that is, in fact, what the standard attempts to do, but it makes a mistake. And it says that nans ignore the sign bit. The way out of this problem would be to obey the sign bit, and then nan I minus would be a different thing from nan I plus, and you would get the ordering that the people who wrote the standard thought they were getting. Abstract 0 has two concrete representatives, minus 0 and 0. Therefore, every abstract 0 orders before and after itself. So here's minus 0 is before 0, but they're identical. And here 0 is after minus 0, but they're identical. So 0 occurs before and after itself. Again, ordering at the abstract level of an abstract 0 is inconsistent. You have to look at the bit patterns to do the ordering. The relational operators less than, equal to, greater than, unordered are incoherent. It's a long story. You need to read the paper. The standard mathematical functions defined in the standard are inconsistent. There is a proof in the paper. I observe that the built-in sorting routines of all popular languages are bugged. And they're bugged because the relational operators are incoherent and because the standard for ordering is incoherent. By contrast, transfloating point arithmetic is logical. All of the proofs of consistency prove that. It's consistent, it's coherent. By coherent, I mean that it plays nicely with real analysis, with physics and so on. It has a tolerance that is twice as fine as IEEE 754 floating point arithmetic in the same number of bits. So in that sense, you get twice the accuracy if you use transfloat. And the transfloating point numbers are physically meaningful. We know what a nullity force is. We know what an infinity force is. We can calculate with these things. We can control machines with these things. We can design machines with these things. How can we design machines with these things? We draw them using geometry. And now that we have transarithmetic, we can calculate them. Well, 2022 was a good year. Work on the Dedekind, Thiago and I published a paper on Dedekind Cuts. Dedekind excluded 3 cuts. Dedekind defined the real numbers. He did it in terms of an object called a cut. He excluded 3 cuts. That gives you real arithmetic. That prevents division by 0. That makes arithmetic partial. If you put Dedekind's excluded cuts back in, so you use all of the cuts, then you get transreal arithmetic. So real arithmetic and transreal arithmetic have an identical basis in geometry, in the solution of equations, and in Dedekind cuts. So I say it's perverse to use real arithmetic when you could use transreal arithmetic, because you're buying failure to no benefit. And I think it's perverse to use IEEE 754 floating point arithmetic in preference to trans-floating point arithmetic. If you use trans-floating point arithmetic, your problems of specification and testing would be easier, and your calculations would be twice as accurate. So in conclusion, IEEE 754 floating point arithmetic could be improved by adopting transreal arithmetic. If you don't want to adopt it, that's fine by me. What do I care? There are various ameliorations you could make to the behavior of zeros and nuns, which would make IEEE 754 more coherent. All accusations against transmathematics relate to transreal arithmetic and were first made around 2007. There have been later criticisms of it. People argue with good mathematical reason that transreal arithmetic has this or that property, which is nice or nasty or whatever. Criticisms are fine. Unfounded accusations are not fine. All but two of the accusations have ceased. One of them is that nullity is an error value. I state that's false because nullity is a physically meaningful number. And I don't intend to do any more than simply state that. It's recorded. That is my opinion on nullity. There is a live accusation that transreal arithmetic plagiarized IEEE floating point arithmetic. There is no evidence that this is true. People putting forward this accusation give no evidence. And there's a lot of evidence that it's false. For example, read the paper. And the question is, what am I going to do about this false accusation, which is extremely damaging? It prevents people from taking up transreal arithmetic. People in British universities are afraid to teach transreal arithmetic. They're afraid to apply it in computer science. This is a very bad situation to be in. What can I do about it? And the only thing I can think of is to make a counter-allegation. And the counter-allegation is that the people alleging plagiarism are ignorant of the facts. So what I've done now is I've given a counter-allegation. And anyone assessing this situation needs to consider both sides of the argument. And I'm making a very strong allegation. If you say I plagiarize IEEE float, I am calling you ignorant. We'll see where that gets. So I believe that using real arithmetic in preference to transreal arithmetic is perverse. It's guaranteed to fail. It damages our technology. It damages our science. It makes all of our societies weaker, more prone to error than they need be. So I'm championing transreal arithmetic, championing transmathematics. That brings my presentation to an end. Right, we have 5 minutes before Walter is supposed to speak. Does anyone want to ask me any questions on what I've just presented?
James,
yeah,
I've got a question for you. Have you written out in detail a reconstruction of Jacobi's method from 1846?
I haven't, and I could do that. The basic issue is that Jacobi's original algorithm is the same as the modern one that you look up in books, except that he does not switch to using the cotangent. He always applies the tangent. And people who do not have access to transreal arithmetic would suppose that dividing by 0 is an error, and so they would want to do something about it. And the modern algorithm says use the cotangent. If you use transreal arithmetic, then the division by 0 is perfectly straightforward. The tangent, the arctangent of 1 over 0 is perfectly well defined. The arctangent of -1 over 0 is perfectly well defined. You just plow on. So what it amounts to is that when you have a division of a number by 0, you perform a rotation, Jacobi's algorithms in terms of rotations, of 90 degrees. And it converges. So the difference is that Jacobi did not outlaw division by 0. And he used tangents everywhere. He never switched to cotangents.
It seems to me that it would be worth taking the trouble to write out that argument in detail for scrutiny.
Yes.
And there are precedents, and there are some very interesting precedents in analysis, because theorems about the convergence of functions and the uniform convergence versus convergence go back to Cauchy. And the problem was that uniform convergence was the thing that corrected the theorem of Cauchy. But if you rebuild the argument of Cauchy using an infinitesimal analysis, then you can coherently, using the modern framework of infinitesimal real line number, a la Abraham Robinson, to show that the argument of Cauchy would make sense if you are fluent in your infinitesimals. And that was first written out in the British Journal of Philosophy of Science, I think, many years ago. And I think one or two people have subsequently re-examined it as pucker historical analysis, if you like. So it could be the case that if you were able to go through the Jacobi paper and lay before a modern audience what goes on, and certainly what goes on if this switch is not performed, you could also smuggle in to an unsuspecting historical audience, never mind some unsuspecting historical referees, a great big dollop of your argument about 0 over 0.
That is an excellent idea.
Well, it would take a certain amount of effort to dig out the paper and do it, and to write it up in without having a sense of, if it all works out, then you have to write it up as a sort of journey of exploration, that there is indeed a different algorithm from the standard, that indeed the algorithm works under a certain interpretation, and that we have tools to formalize that interpretation, namely your system. That would be, I think, a very worthwhile thing. I mean, 1846 is a long time ago.
Yes.
It is 30 years before Dedekind ever wrote anything on the subject. So that's my comment anyway.
Yeah, that is an excellent idea. I think you've given me the idea for my next paper. Let me immediately say that Jacobi's original algorithm is faster because in the innermost loop there is no switch, so that saves you time. My guess would be it's less accurate if you're pushing tangent all the time instead of switching to cotangent, but I would have to look.
Well, I would suggest that you look up this analysis of Cauchy's convergence theorem using non-standard analysis to see the first and second papers that attempted that, to get into the swing of how they bring this question up. That's what I would suggest.
Yeah, that's brilliant.
I'll try and find the papers and email you some reference.
I still would have a question to you. Is that okay?
Yeah, that's fine.
So I'm slightly worried about this nullity versus error or error element. So clearly, if you would admit that nullity is an error element, you get a simplified philosophy of the thing. It may be superficial, your point of view, but this whole connection with geometry is a philosophical overhead, which might be dropped. Not that it's better to drop it, but in the most simplistic view, nullity is an error element. And I wonder if there is a way to, from your point of view, to understand this as a legitimate perception of transreal arithmetic.
I already completely accept that as a way of setting out formal arithmetic. The difference for me comes in physics, where if you have an error value, you give up trying to control things, you give up trying to analyze, whereas I continue controlling, continue analyzing. So the issue for me is that in the application of transreal arithmetic, nullity is not an error value. I have no problem at all with people who say that nullity is an error value within the formal arithmetic. That's fine. Call it whatever you need.
Right.
So
accusation is sort of complicated. Formally, it's not an accusation that you would be worried about.
Yeah.
But it's an underestimation of the potential of the thing.
Yes.
Right.
And the potential is in applied mathematics, not in formal mathematics, not in pure mathematics. It's a question of physics, not mathematics.
Mm-hmm.
I'm being secretly supplied with a mug of tea.
Yet another question is there still any sort of high-profile researchers who produce these kind of accusations against your work?
Certainly not in writing. You're aware of the written accusation because it's in the paper. Several mathematicians, including quite well-known ones, have asked me, is transreal arithmetic the same as IEEE float? So that's not an accusation, but that is a question which could have arisen from the accusation. So I would like it to get out there into the world that no, they are different things, so that people stop asking this question and treat transreal arithmetic on its own merits, whatever they are, good or bad. It is different from IEEE float. Deal with it on its own merits. And partly what people are doing is they hope that transreal arithmetic will be the same as float, so they don't have to think about it. But if it's different, then there is an obligation arising to think about transreal arithmetic.
But that's having said that, there is no individual who one could write to or write about in relation to these accusations.
Regrettably not. You're aware of the written claim. That's the first time I've seen the plagiarism claim written down in 2022. Claim first arose in 2007. So it's taken many, many years for these anonymous accusations, this chatter, to get written down.
And don't you expect that these accusations also will die out, just as a matter of time?
Oh, yes, absolutely. Possibly, IEEE float will be replaced. It is only a computer standard. There are benefits to not doing it. If IEEE float is essentially a US standard promoted by Intel, they're the main drivers of it, an American company. If computer companies from other countries in the world adopted transfloating point arithmetic, they would have two benefits. First, their calculations will be twice as accurate. So that makes it worth buying their chips rather than Intel chips. And secondly, they have a marketing opportunity. They can say Intel chips have an astronomical number of error states. Ours have none. So, and I do have some experience of this. So there was an electronics company that assessed transrational arithmetic for use in their electronic devices. They made navigational equipment. And they decided that transrational arithmetic would improve all of their product line. And it would reduce the amount of circuitry by 80%. That's huge. And the reason is that standard computers use 2's complement arithmetic, mentioned in the paper, which has one more negative number than positive. And that's a problem if you're building navigational equipment because you go around in circles. And so you need to correct this situation. But you can't do it with a computer chip because they all work the same way. You have to put in bulk circuitry to correct for this extra state. And that bulk circuitry is 80% of the circuitry of their devices. So they were very keen to use transrational arithmetic, but they couldn't because it's not implemented as IP cores in FPGAs, because there's no compiler stack, software tool stack to use it. Now, if an FPGA manufacturer were to adopt transrational, well, it would be transinteger, trans-2's complement or transfloat arithmetic, then that would be another way in which this arithmetic could be used in commercial applications, might gain traction, might replace IEEE 754. But it's going to be a mighty long time before any of those things happen.
The physicists developing their own hardware for
yes, they are.
special applications.
Yes, they are. And parallel computers at
yes.
one stage used cores that were not IEEE 754 compliant. And the early Cray computers used their own form of floating point arithmetic, which was faster and used less power. So high performance computers quite often do not use IEEE 754. There has been a move toward putting IEEE 754 into high performance computers. And partly this is a marketing ploy. It's quite hard to implement 754. It brings a barrier to entry against new manufacturers. So an absurd marketing reason for having IEEE 754 is that it's so damn complicated. And it's so damn complicated because it's incoherent. And it's really hard to implement something that gets everything wrong in exactly the right way.